Okay, guys, today I'd like to talk about a very important definitions in the mathematical analysis or probability theory, which is the countability. What do you mean by countable? By the mathematical concept, we just define it as it has the same number of elements as the natural number n. Here we will give several examples. Firstly, let's see how to prove this is true. And to show this, I would like to, since they are both infinite sides, and I will use the bijection, which means the inflection and surjection, to prove it using the diagonal method. Now let's draw this picture. You see, this is the I'm n to n. I want to construct this bijection. Then I want to what do I mean by this is 1 to the natural number 1, and 1 2 to the natural number 2, 2 1 to the natural number 3, etc., like 3 1 to the natural number 1 2 3 4. And this diagonal has some magic. You know, each diagonal, their summation of m plus n equals the sum of the m and n are the same, and is just be the next number of this sequential number of the diagonal. For example, for the 3 diagonal, 1 plus 3 is 3 plus 4, 1, which is 4. And injection, I mean, if I choose two natural number n, which is n1 and n2, since each natural number will corresponding to only one of these. One of these, I will say is injection. For the surjection, I will say for every number in n, there always exists an mn that corresponding to that, because they are both infinite, and this diagonal could be like this forever. And so I have constructed a bijection. So it's this bijection means they have the same elements. And here I could also further construct the specific mapping from n to n. Here the method 1 is I will choose the number of all points before the m plus n minus 1 diagonal, which is what I mean by this round 1, round 2. I will choose for 3 the number is 3, and for 4 the number is 1 plus 2 plus 3, which is 6. It's like 1 plus 2 plus 3 is a arithmetic progression. 1 plus 2 plus 3 plus plus 2 m plus 1 to n, and I use this formula, which is the first term plus the last term times the number of the terms over 2. And you know the first term is 1 because the first diagonal only have 1, and this corresponding to the natural number 1, and the last term is just the m plus n minus 1 diagonals number minus 1, and the number of the terms is just also this, and I have this, and for example, if I take m plus n minus 1 equals to 3, I will say and this is just plus 1, this is plus 2 plus 3, this is just 2 3 plus 1, this is just 3 plus 2, this is just 3 plus 3, and etc. etc. And another method is similar. I will not take before, but also including this. Then I will have also the same idea. And here I correspond to this, and if I want to know this, I just minus n and then plus 1. It's also the same. So I have successfully have this mapping or this mapping. They are totally the same. And similarly, we could also give another example, which is the integral d is countable. I also will prove this. I will draw this. Also, it's not good down, but it's totally the same idea. And in each point in this integer of the axis should correspond to one natural number. And if I say this is 1, this is 2, this is 4, I must say this is 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, then I will just say this will correspond to each even number, and this is odd number. And based on this, I have constructed my sequence successfully. Here, furthermore, another example is to prove R can be placed in one-to-one correspondence with a subset of N. And I want to show R, the whole real number is not countable, it's uncountable. And this idea is from the Cantor. Cantor is a very genius, very intelligent mathematician, and he's really a genius that no one can understand him. But his creativity is very powerful and interesting. Now let's understand his idea. He said we could write each real number uniquely as a decimal, and this decimal should always choose in no terminating version. And I will restrict this R to the closed interval from 0 to 1, and I will say this is uncountable, and then I show R is uncountable. Now, if I suppose this is countable, then I should say, and also each xn could express as this way, and I will list all of them since it's countable, but also this ans from 0 to 9 will randomly choose it from it, and if it's countable, I could list all of them in this kind of shape. But when I write y equals to 0.b1, b2, b3, where bn equals to 9 minus ann, which is this diagonal term, this y is not in this group, so it is already a contradiction, because I have already said this is all number in this one, and y is not in here, but y also follows this construct. So why this is reasonable? Because our suppose is that it's not it's countable. So we suppose it has a bijection from n to r, And our sequence from x1 to xn is like this from f1 to fn. And since it's a bijection, so this sequence should contain all of the real number. But y is also a real number and follows that expressed in a decimal way, but it's not in here. So it's not a bijection, and our suppose is not true. And actually, when we say a set is countable, we just mean that all elements in this set can be laid as a sequence. This is because just what I said before is a bijection from the natural number to this side. Next, I'll introduce the concept of the counter set, which also from the idea of the genus Cantor. And it's an interesting set that we always for 0 to 1 this interval, we always equally depart it in 3 parts and always remove the middle part. And if we do this the second time, it's like that, and the third time, and this is just that. And here I call this D3 because I do the action 3 times. I define a counter set to be the intercept of all Cn. Now, first issue is uncountable because each x in this set can be expressed in a ternary way. This ternary means this decimal is just 3 because I just say is if I do this is 0.01, this is 0.02, and this is 0.21, 0.22, and I also could say 0.22222 equals to 1. Oh no, just approximately equals to 1. Now suppose it's countable. Following the previous idea, we could depart it. We could list it in a sequential way, which is this. And I could always I could always write 1 equals to 0.b1, b2 from the bn, where bn equals to 3 minus ann, 3 minus ann. I like that. And previous is 9 minus ann, right? And bn is not equals to each ain. Yeah. And but it's an interesting side because although it's uncountable, it is a non-side. Here, the non-side comes from the measure theory. The total length of it is 0. No, it could say be 0. Firstly, it could be for the total length. Because for the 0 to 1, it has the length of 1, and I will minus the sum from n equals to 1 to the infinity. And this sum is all I removed because each time this length is this, and I do this. And this is just have 2 power n minus 1 this thing because each time what I remove each interval remove the length is 1/3 power n, but each time the total part of this is the number of 2 power n minus 1, right? And I plus this using the geometric theory. I have proved that it's 0, or the second method is from the major series concept of the null side. The null side here means for any epsilon greater than 0, there is a countable collection of intervals, In, such that the A is in this union of all intervals, this collection of intervals, and this collection of intervals that cover A has a very small length, which is expressed as the shape of less than epsilon. Therefore, instead of counting the term of the term that I remove, I could always choosing the term that I not remove, which is just the 2 power 3 power n, because it's just I do each time there are 2 power n's come out, and each length is just this. And here, by the Archimedes theorem, for any epsilon greater than 0, I can always choose n very small, that 2 over 3 power n is less than epsilon, and since C is in the Cn, and Cn consists of a finite sequence of the intervals of total length less than epsilon, and C is actually a non-side. So why is the counter side null, even though it is uncountable? Clearly, is the distribution of its point. The fact that it's spared out all over 0.1, which causes the trouble. This makes it the source of many examples, which show that intuitively obvious things are not always true. For example, we can use the counter sign to define a function called Cantor-Lebesgue function with very old properties. And next, we further introduce a very magic charismatic function called Cantor-Lebesgue function. It's a function defined on the counter side, and it only defined on the counter side with the length. No, not with the length, because it's a null side. I mean, it only defines on if it is removed, we will not increase this function. But if it's not removed, for example, maybe on this interval, it increases totally with a length of 1/4, and it's because I forgot to define for 1 f1 equals 0 and f0 equals to 0, so it increases from 0 to 1 in a y-axis, and so they increase similarly. So in this closed interval, it increases from 0 to 1/4. So how to define it more rigorously? Now let's say Bn equals to an over 2, and x is just 0.A1, A2, an equals to 0 or 1 or 2. Now let's define n as the first index n for which an equals to 1. This means for an equals to 1, for example, 0.1 here, and 0.1 here, and 0.1 is here. Why is that? Let's firstly begin our definition. And now we let Bn equals to an over 2 for n less than n, and bn equals to 1. This means n equals to n. And we define f of x equals to. Why is that? Because here, what we focus on is after a period of the set that's removed. I mean, if it's from 0 like that, we remove that and we consider here. We will know that it's 1 over 2. And but why is 1 over 2? Because this is 1 over 2, right? But here we like here is how to express this in a decimal way is 0. This is 0.2, right? It's now it doesn't have the first index of the appearance of an to be 1, right? So now we further define if there are no decimal point that has an to be 1, we just define n equals to infinity. In that case, we have f(x) equals to infinity from which equals to which is equals to
你看那手机上多少钱了呀？
你的？
你呢？民生银行。
什么民生银行？
So in that case, it is 0.2, right? And so it doesn't have any a that with the appearance of an to be 1. So now we define if there are no decimal point that has 1, then we define n equals to infinity. It's reasonable, but right? Because we just think it never appear 1, but in the infinity point it appears 1. And here we just write down f(x) equals to r 2 times 2 divided by 1, because the first b is
2.8.
because b1 equals to 2 over 2. A1 equals to 2. Substitute a1 to be here, we have 1, and it's here. And from 2 to the infinity, we have here. And this is calculated by geometric series. So it's 1 over 4. So we know it's 1 over 2. And it's actually 1 over 2, right? And so we have this, the third special n, and the second special n is this, and the very common term is that, because it's like when we have this have a total 1 over 2, 1 over 2, and from here, if it originally had 1 over 2, and now we will divide it, and each time if we have an equals to 1, we just should times this, but each time if we have n equals 2, in that case, So, and also it's reasonable because this definition could be tested on this. We could express 1/3 in the two way. One is 0.1, and the other is the other is 0.02222, and it's just the infinity. And then we have that, and they are the same, right? We also could say it's 0.2 or 0.12222.
不过他这些都弄着吧，他没砸盘，国家那个。
It's reasonable. So the magic here that it is non-side, and the Cantor-Lebesgue function increases from 0 to 1 over this non-side, and this is its property, which means the supremum of fy equals to fx because it only increases in the counter side. And we have f prime x equals to 0 almost everywhere because we based on our definition, right? And however, it increases, so it's like just like that was later. That was dire. It's just you can't imagine this kind of stare because it's like it increased very fast, but its derivative actually equals to 0 almost everywhere. Because and furthermore, it's not satisfy the Newton-Leibnitz formula because we know from 0 to 1 the f prime x dx equals to 0, but f1 equals to 1, f equals to is 1, and they are all the same. It's very interesting.